Okay, so in this series of videos, which span 2 chapters worth of material, we'll be taking a look at the mechanics of rigid bodies. And in this chapter, we're going to be taking a look specifically at planar motion. Now, it should be observed that there is truly no such thing as a rigid body. You can't have rotation without deformation. At the end of the day, it's adjacent molecules tugging on each other that are what make anything rotate. But it's a very useful fiction. Okay, so with that said, let's go ahead and take a look at the center of mass and how to go about finding it. Now, we've already visited this before for a collection of point particles, and we're just going to extend off of this definition. We said it's the sum of the weighted averages of the positions. Sorry, well, it should just say it's the weighted average of the positions. So MIRI summed over the mass of the whole thing. Now, if we have a lot of particles for the region we're looking at, so say we're looking at a microscopic object, you're looking at 10 to the 23rd or so particles all jammed in there, we can begin to approximate this by assuming that the stuff is smoothly smeared out. What do I mean by that? Well, if you are at a beach and you basically put your head right up to the sand, you can see the individual grains really well. But if you're walking up to the beach, you'll just see some sort of continuous blur sandy color thing without noticing that it's made of distinct grains. And that's the idea we're going to do here. So we're just going to pretend that it's all uniformly smeared out. So in that case, we can approximate, and this is strictly an approximation. To do it right, you should be adding over the molecules, but life gets short. We integrate the position of all of our differential mass elements, and then we divide by the total mass. Now, the first step is always to write some sort of integral dm. But the trick is figuring out how to express that dm. Typically, you can't just integrate over mass. You're going to be integrating over some sort of coordinate, which means you need to transform it into something. So if it's, say, a volume, usually you'll express your dm as some volume density times some differential volume. Likewise, if it's an area, you would express your dm as a surface density times some differential of area. And finally, if it's on some sort of a line or a curve or something like that, you would express as a linear mass density times some differential of length. So this is not a p, this is a rho, sigma, lambda. And those are standard in almost every text except for one very popular introductory text series that for some reason likes to use eta rather than sigma. Okay, so some of this we can kind of figure how to do if, say, we have a composite object. And it's one whose center of mass, made up of pieces whose centers of mass we understand well. So let's say Now I've got two circles that are just touching like so. There's the centers of mass of each of those. You can just go ahead and find the center of mass of these two centers of mass, just treating them as point objects. So sometimes you get lucky and you can do something like that. And so for instance here, we can kind of take that idea into the line of differentials a bit. Let's find the center of mass of a triangular lamina. So, yeah, I can draw better than that. Come on. That's not too bad. I want this to be a right angle right here, and then these are 45 and 45 just to make it a little easier. And while we're here, let's go ahead and insert a coordinate axis. So put the origin here, x-axis, y-axis like so. And we know that the center of mass of any differential strip, so let me just make a little differential strip here, we know the center of mass of it's right in the middle there. So, so the differential of area here will be, well, this width here is 2y, the way I've got it rigged up, because we're running from minus y to y along the x-axis. And it's of height dy. So it's 2y dy. Alright. So from the symmetry of all this, the x-coordinate of the center of mass is 0. And to get the y-coordinate of the center of mass, we'll go ahead and follow our recipe. So we'll say ycm equals, we'll integrate our y-coordinate with respect to our differential of mass, which is sigma dA. And then we will integrate just sigma dA to get an expression for our mass. Okay, so then ycm will equal, putting in for what our dA is, 2y dy, our limits of integration are going to run from 0 to y. So 0 to y, so we have y sigma 2y dy over integral 0 to y of just plain sigma 2y dy. The sigmas and the 2's cancel for what it's worth. And so we're left with integral 0 to y dy, y squared, over integral 0 to y dy of y. Okay, and we know how to evaluate those. The numerator will be y cubed over 3, and the denominator will be y squared over 2. So we can cancel, cancel. This leaves us with 2/3 y. Okay, so that's how you go about finding moments of inertia for continuous objects. And if need be, if it isn't so nice and symmetric, then you just plain have to integrate over x and y individually. Alright, so now let's go start building up the machinery for moments of inertia. Very roughly, we know that it tells us how hard it is to twist an object. So let's look at our thin lamina here. We'll make it some sort of a peanut shape. Like so. and fill in the sides. Okay. And let's say that this z-axis right here is my axis of rotation. And we'll go ahead and rotate like so. So then omega points up like that. And so we can write it as being equal to k hat times the scalar omega. All right, now if we look at a particular mass point, say right there, let's choose a different color, say right there. So I'm just looking at some small piece of mass right there. It'll be at position Ri, and it's moving tangent at velocity Vi. Now here, and this is true in general, we can express Vi as omega cross Ri. You should take half a second here just to convince yourself that the cross product does work. This is true in general. All right, so now let's go ahead and find our rotational kinetic energy. So T rot will equal, we're going to have to sum over all of our masses. So sum over I, 1/2 mi Vi squared. Remember that to do Vi squared, that's Vi dot Vi. Okay, so putting in for what that is, we'll now have a sum over I. Can pull the 1/2 out for what it's worth. Mi, and then I'll have omega cross Ri dotted with itself. Okay. So we have an identity for that. And that it's equal to 1/2 sum over IMI of omega squared Ri squared minus omega dot Ri squared. Now this second term here goes to 0 because you can see omega and the Ri are perpendicular in this case. So we can write our rotational kinetic energy, T rot, is 1/2 times the sum over I, MIRI squared, times omega squared, just pulling the omega squared out of the sum. And as before, we can look at this much of it right here, and we will define that as the moment of inertia about the z-axis. Okay, so with that change of notation, we can say that T rot is equal to 1/2 Iz omega squared. All right, now let's go ahead and connect that to angular momentum. So the angular momentum of any mass particle is going to be r cross p, so we'll sum over all of them. Ri cross pi to get the total. So that'll be equal to sum over I, Ri cross mi vi. And I can pull that m out of the parentheses, but not out of the sum. Ri cross VI, like so. And then we can put in what our VI is. It's omega cross Ri. So sum over I, Mi, Ri cross omega cross Ri. And so here's a good time to invoke the back cab rule. Sum over I, Mi. So back B is omega times A dot C Ri dot Ri minus cab, so C is Ri, times A dot B Ri dot omega. Now once again, Ri dot omega is 0, so the second term drops. Ri dot Ri is just plain Ri squared, and so we have that L is equal to sum over I MIRI squared times omega, which is equal to IZ times omega. Now, let's think about applying a torque here. So remember, we said that N is equal to dl dt. That's the rotational form of Newton's second law. So that's d dt of Iz omega. Now, if the object is rigid, which is what we're looking at here, we can pull it out. So then we get that it's equal to I alpha. All right, so the moral of the story here is that our moment of inertia about the z-axis is playing a role for rotations about the z-axis that's similar to the role that, say, the mass plays for translations. Now, there are a couple of caveats here. It's not as nice as the mass. Our moment of inertia about the z-axis depends on not just the mass, but also its distribution. And it also depends on our choice of rotational axis. So whatever, if it rotates about a different axis, we have to totally recompute our IZ. So it's a helpful analogy, but it is going to be a little harder. Okay, so let's look at calculating these moments of inertia. Calculating moments of inertia. Okay, so we remember that from before that if it's point particles, we just say sum over I mi Ri squared. So taking the same playbook that we had before, if it's an extended body, we can do the same approximation and say Iz is equal to integral dm r squared. And it's the same prescriptions for dm that we did before. So let's go and visit our friend, the thin rectangular lamina. So, oh hey, we just happen to conveniently have a coordinate system just hanging around. X, Y, Z, like so. here's my lamina. It's in the xy plane. Like so. And its dimensions are a by b. If I did even a half decent job of drawing this, which I know I didn't, we're going to be running from minus a over 2 to plus a over 2 in the x, and minus b over 2 to plus b over 2 in the y. All right, so let's go ahead and compute our moment of inertia. So this will be integral dm r squared. Okay, now this dm is going to become a sigma dx dy, because that's what we get when we pull out some little differential of area. dA will be of width dx and length dy. So let's just go ahead and put in what it all is. So integral. So my r squared will be x squared plus y squared, and then my dm is sigma dx dy. So my integral over x runs from minus a over 2 to a over 2 minus b over 2 to b over 2. Excellent. So I can go ahead and fold both of these integrals and just run them from 0 to a over 2. So I'll pick up a factor of 4 there, and I can pull the sigma out of the integral. So 4 sigma, and now my limits are 0 to b over 2, 0 to a over 2 of x squared plus y squared dx dy. Okay, so first we need to evaluate the x integral. So this will become 4 sigma integral 0 to b over 2, and the x integral is going to become x cubed over 3 plus y squared x. We're going to evaluate that from 0 to a over 2. And we still have our integral over dy to do. So 4 sigma. This is going to become, let's see, a cubed over 8 divided by 3 is going to give me a cubed over 24. So integral 0 to b over 2 a cubed over 24 plus a over 2 y squared dy. Okay. If I want, I can cancel out one factor of 2, so let's just do that. Alright, and actually let's do that in red just so we can see what we're doing. So canceling out 2 leaves me a 12 there, leaves me a 2 there. Alright, now we go ahead and evaluate the integral over y. So now I got 2 sigma, and so I'm going to have here a cubed, supposed to be an a cubed over 12y plus a times y cubed over 3 evaluated from 0 to b over 2. So let's see, what am I going to pick up here? I'm going to get 2 sigma a cubed over 12 times b over 2 plus a, and then this is going to give me b cubed over 2 cubed, so b cubed over 8, and then we're divided by 3, so it's b cubed over 24. Alright, and once again I can go ahead and cancel off a 2. So it becomes 2, cancels that 2, leaves that being a 12. Alrighty then. So this isn't looking as bad as you might think. I'll pull there's a common factor of AB in everything. So I'll just pull that out. Sigma AB times, and then there's also a common factor of 1/12 that I'll pull out. And I'm left with A squared plus B squared. Now this sigma AB is just the area of the square, and sigma is the surface mass density. So this whole bit right here is just plain the mass of the lamina. So with that identification, whoops, we get IZ equals 1/12 m times A squared plus B squared. And that's how you do that kind of thing. So it wouldn't be a physics class if we didn't revisit our friendly Atwood's machine to see where this sort of thing might take us. So, all right, now we're going to have a massive pulley. So we'll have mass MP, radius R. We'll have a big mass M hanging off on this side and a small mass M on that side. And we're going to go ahead and say that we're going to just let big M drop some distance h, so this will go up by that same distance, of course. And we want to find the speed of the blocks and the angular velocity of the pulley. All right, so we can go ahead and conserve energy here. So our energy losses are going to be just big mgh, and our gains are going to be little mgh plus 1/2 big mv squared for the kinetic plus 1/2 little mv squared for the kinetic. But now we pick up a rotational kinetic energy term, 1/2 I omega squared. Okay, so we can rearrange a bit. We get m minus m gh equals 1/2 m plus m v squared plus 1/2, and the moment of inertia for our disk is going to be 1/2 mr squared. So we pick up another 1/2 mp r squared times omega squared. Well, you look at this and say, zounds, r omega is v, so this is v squared. All right. So I can take this a little further and write this as 1/2 m plus 1/2 the mass of the pulley, v squared. So then I can solve for both omega, since v is equal to r omega. So I'll just leave that for you to turn the crank there. Is equal to root 2 m minus m gh over m plus 1/2 the mass of the pulley. Okay. Now, just like before, if you have a composite object, so let's say I got some sort of blob, and then say a nice little ring just sitting on the blob, and they share a common rotational axis. All right, let's call the ring object number 1, call the blob object number 2. We can say that the moment of inertia of the system, IZ, is equal to I1 plus I2 plus and so forth if I've got more than just two objects making it up. Okay. Now, I know from your lower division courses that you've heard of the parallel axis theorem before, but did you know there's a perpendicular axis theorem? Why, yes, there is. This only applies for thin lamina, or for a plane lamina. So it isn't as it is broadly applicable as the parallel axis theorem, which we will get to shortly. So if you noticed with your z-axis here, that's the one that's perpendicular to the plane. That was equal to sum over I mi r I squared. And we found that that was sum over I mi xi squared plus yi squared, thanks to Pythagoras. Well, I can separate that out as being, and I'll write this a little awkwardly, it'll make sense in a moment, sum over I mi yi squared plus sum over I mi xi squared. And what's up with that? This is the moment of inertia about the x-axis. That's the moment of inertia about the y-axis. So if you have a if you have a thin lamina, you can write Iz is Ix plus Iy. Again, that's only true for thin lamina. But it is a handy result. Okay. And I can say this, by the way, because for instance, Ix would be sum over I mi times yi squared plus zi squared, but all my z's are 0. That's how this works. Okay. So we can revisit our friend the thin rectangular lamina. So this is part 2. So again, same illustration as before. So x, y, z. The lamina lives in the xy plane. And again, we'll run from minus a over 2 to a over 2 minus b over 2 to b over 2, like so. But here I'm just going to go ahead and find me moment of inertia about the x-axis. So what I can do is I can take a long, thin strip like so of width dy. So my dA here will be equal to a dy. So this will be integral. So we'll have y squared plus z squared dm, right? But the z squared is going to be 0 since it's thin lamina. And we can express that. It'll be integral minus b over 2 to b over 2 of y squared times sigma a dy. Alright, so I can fold the integral again. So it pulls out 2, and sigma and a are both constants, so I'll pull them out too. Integral 0 to b over 2, y squared dy. I know how to evaluate that, so I get that Ix is equal to 2 sigma a times y cubed over 3, you've evaluated from 0 to b over 2, so this will be b cubed over 8. Divided by 3 will give me b cubed over 24. 2 sigma a b cubed over 24. I can cancel off a 2 there, leaves me with a 12. And same trick as before. I can write this now. So Ix equals 1/112th. 1/12th, I mean, sigma AB times B squared. And I wrote it that awkward way because I can recognize that that's the mass of the whole thing. So I get that the moment of inertia about the x-axis is 1/12 mb squared. I don't think it's any great stretch to show to believe that you could show. There we go. So similarly, Iy is equal to 1/12 ma squared. So we can get Iz without thinking too hard. We just add up Ix and Iy. So that integral we did before turned out to actually be unnecessary. It'll be 1/12 ma squared plus b squared, which is what we got before. Okay, oops. So now, with that, let's go to the more applicable parallel axis theorem. And this is for any rigid body. All right, so since it's any rigid body, let's go ahead and draw one. So I'm imagining some sort of schmoo-shaped blobby thing like that, maybe. I don't know. I'm going to try to get some 3D effect here, but that's about as good as I can do. All right, so let's say we know the center of mass, and it is located right here. All right. So with that, we can locate some point mass right here. This will be the ith point mass. So mi. Its regular coordinates will be ri, and in the center of mass will be located at rcm. And this will be located at ri bar. Okay, in the center of mass coordinates. So with that, let's go ahead and plow ahead and compute the, well, I suppose I should label my axes. I'll do x, y, z like that. Let's go ahead and compute the moment of inertia about the z-axis. All right, find sum over I, mi, xi squared plus yi squared. And we can break that apart, sum over I, mi. Xi we can write as xi bar plus xcm squared. Then we have plus yi bar plus ycm squared. Okay, so we can take that those squares and expand them out further. So we'll have sum over I, mi. We'll do the four terms, and I'll write the sum over I, mi for each of the four. So this first bit here is going to give me an xi bar squared from here. And then doing this one here, I'll get a yi bar squared there. Similarly, when I FOIL these, I will get a xcm squared and a ycm squared. So sum over I, mi, xcm squared plus ycm squared. And then I still have two more terms. I have the cross terms from this guy here, so I'll have a 2. I can pull out the xcm because it's a constant. I mean, I could have done that here too. 2 xcm, and I'll have a sum over I, mi, xi bar plus 2 YCM sum over I MI YI bar. All right, but these two terms here, I don't have to sweat. They both go to 0 because the sums are locating the center of mass with respect to the center of mass, so that will be 0. More interesting is to interpret these two terms, 1 and 2, and we realize that 1 is the moment of inertia for an axis parallel to z through the center of mass. And 2 is the moment of inertia for a point mass about the z-axis, located at the center of mass. So the moral of this, so say here's another one of my blobs. Let's make that the z-axis. Let's say the CM is located here. I just throw in another axis parallel to it, called the distance between these L. Let's say it rotates about the z-axis like so. We end up saying that the moment of inertia about this z-axis here is equal to the moment of inertia about the parallel axis that goes through the center of mass plus ml squared, where we treat the whole thing as a point mass located at the CM and rotate that point mass about the z-axis. So as an example of that, let's go ahead and look at a thin rod. So let's go ahead and so if we go and look, you can treat the thin rod as a lamina of basically no y dimension. And so if we say the whole thing is of length L, we get that the moment of inertia through the center of mass is 1/12 ml squared. Now, if we were interested instead about doing it about the end, then we would say that I equals ICM plus m times this distance, which is L over 2 squared. So it'll be 1/12 ml squared plus 1/4 ml squared equals 1/3. Oh, ml squared, which beats taking the integral again. Okay, in many texts, they prefer to actually, you know, this I think is going to be a good breaking point right here. So on the next video, we're going to pick up introducing the radius of gyration, and we will analyze the physical pendulum.